So it's nice to have all of you here, and I hope you will get something out of this. As Subodh said, I'm sort of substituting for Priya Mahadevan, and as a result, I haven't had much time to prepare. I had some time, but so here and there might be a little waffling. Let us see. Okay. All right. So let me begin. First of all, let me ask you all, which name do you associate with statistical mechanics? In the 1800s, somebody, yes, say it loudly, Boltzmann. Huh. And there's a famous constant which he introduced. What is it called? Boltzmann constant. Actually, there's a very interesting story, which I will not tell right now. When it was first introduced, it was called, you know what? It was called the Planck constant. Planck was insistent it should not be called a Planck constant. And then anyway, a few years later, he had a constant of his own. You've heard of it, no? 8. But Boltzmann had his constant, K. Does anybody know the value of the Boltzmann constant? Yes, you said minus 23. That's because you're using joules. When I grew up, we used to use ergs. So in my units, 10 to the minus 16. But it doesn't matter, 1.38. Okay. But actually, it's not a conversion. Temperature is another way to measure energy. So that's why I wrote down something on the side there. That 1 electron volt, which is a unit of energy which you are familiar with, you should know how much it is in degrees Kelvin. Okay, answer is there, 11,600. It's about 12,000. Okay. So what is the temperature of the sun? Does anybody know? Surface temperature? Sorry? 6,000 Kelvin, which is smaller than this. So, okay, but that corresponds to like yellow light or something. So if you're using an optical unit, you can use this as a conversion, 1 centimeter inverse. So this is just background that you should know the values of something in temperature, And coming back to magnetism, in the lecture we heard in the morning, we talked about a Bohr magneton and a field, magnetic field. So I've put down, so if you have 1 Bohr magneton and 1 Tesla, Tesla is a unit of magnetic field, correct? How much is that in degrees Kelvin? So 0.67 degrees Kelvin. So remember that. Okay, so it's a relatively small energy. That if you put on a field which is quite large, 1 Tesla, that's a relatively small energy, and therefore room temperature or something like that, which is 300 Kelvin, would be much, much larger than that. And so in that Brillouin function that we were talking about, that would correspond to the high temperature limit if you are dealing with room temperature. Okay, this is sort of just to get you a little acclimatized with, what is going on. Right. Now, please come in front. Yes, thank you. Front. Yeah. Person on the phone, please come in front. Come in front. No, yeah. Okay, thank you. No, so you all are all there at Chandan Dasgupta's lecture in the morning, and more or less the last formula he wrote was this. Magnetic susceptibility in zero field is given by a formula which says that if you have free moments, they vary as 1 over T, the susceptibility, and as he mentioned, and it's very important, the factor in front tells you about the multiplicity, the spin multiplicity, because it's not all the time that you have a single electron. Sometimes you have a bunch of electrons acting together. So this is, and then they act together as if there's one large moment. So my lecture today is going to be a little bit about what are these large moments, how do they come about. This is part really of atomic physics and spectroscopy, but it's worth knowing anyway. It doesn't matter what you call it. It's useful for magnetism. Okay, so let me tell you a couple of experimental facts. if you take manganese, manganese is a magnetic ion, and you have a few manganese ions or atoms in copper. Copper, as you know, is a metal, simple metal, and you take maybe 1/10 or 1/100th of 1%, so quite a small fraction of manganese ions. Copper does not have a localized moment, so it will not respond in the paramagnetic way that was described by Chandan, but the manganese would. And so if you look at so it turns out that experimentalists, when they look at this formula, what would you and I do? We would plot chi versus t. But they say they prefer straight lines, so let's plot chi versus 1 by t. Okay, so here, in fact, they plot 1 over chi versus t, I think. Okay, and the data is remarkably straight. Oops. Okay, I mean, I'm not drawing it well, but it's a very good straight line. So first of all, it says you have a Curie law, which is not surprising, because you have these atoms giving a, okay. But if you increase the concentration a little bit of these, this is at low concentration, okay, so okay, and this is at higher concentrations, few percent. Now I'm plotting not 1 over chi, but chi versus t. What you see is, so chi versus t would be like a hyperbola, right? Would you agree? Come in front, please. Yeah. Can you also come in front? Yeah, yeah. Whoever's in the last row can come in front. I mean, sorry. Yeah. Okay, good. Thanks. Now, so I'm saying, had you plotted chi versus t, that would have been a curve going that way, like a hyperbola, y equal to 1 over x, right? So in fact, you see something like this at high temperature, but then you see a sharp cusp and a drop. Very strange. Why should you have a cusp in susceptibility? It turns out that there's a phase transition here. It's a phase transition of an unusual sort. It's to a spin glass phase. Never mind what it is, but there's a phase transition. And what it indicates is that manganese atoms are interacting with each other. Chandan told you that there are interactions in the Hamiltonian and there is the magnetic field. And if there are basically no interactions, like if there are very few impurities and they're very far away, you get a very good Curie law. But so immediately you are led to two questions. Now, the slope of this curve, look at that formula, will tell you s into s plus 1 over 3, right? And when you substitute into the data, you read off s equal to 5 over 2, not half, but 5 over 2. So that is suggesting that each moment has electrons, but 5 of them are lining up. They're becoming one large moment, and then that is responding. So that's the first question. So I'm not writing in great detail, but moments line up. This is the question why. Okay. So this is one of the questions we'll try to answer today. The other thing that is shown by this is that there is a cooperative effect. There's an interaction effect between moments. Okay, the interaction has a form which I think you wrote down a little bit, but where does that interaction come from? That we need to know. Please come in front. Those who are coming in just now, please come in front. Thanks. Okay. So, how do they interact? Where does this interaction come from? The answer I'll tell you right away, something called the exchange interaction. Exchange. And it comes essentially from the fact that ultimately we have electrons. Electrons are fermions. And Fermi particles, if you write down the wave function of more than one, that wave function, combined wave function of many Fermi particles is anti-symmetric with respect to interchange of any two. Okay, a long sentence, but never mind. There's a minus sign somewhere. Okay, fermions. So how does that minus sign lead to coupling between spins? So these are the two things I want to discuss in today's lecture. If time permits, we'll do more. We'll see. Okay, good. Let me start with this. Where does all this come from? Okay, so yeah. Well, I'm going to skip a little bit. I'll start with this, then I'll go here, and then I'll come back. You know, so we'll see. This is called nonlinear. Nonlinearity in physics is very important, but also to keep interest alive, even in a lecture. So we'll do that. Okay, now. Okay, so how do you write down a magnetic Hamiltonian? Again, this was alluded to by Chandan, and the way to do it is to introduce a vector potential. So we have a, okay, so this setting is the following. You have a system with no magnetic field. Now you added a magnetic field. That magnetic field will do two things because the electron has two attributes. One is a charge and one is a spin. Charge will cause orbital motion, and the spin will cause, well, I mean, some coupling to the field. So what is it? So the way to do it, one way to do it is to ask for the change in the Hamiltonian due to adding the field. Okay, so for instance, the momentum P in P squared by 2m will go to Pi minus Qa by C. A is the vector potential here. Yes. We will come to that. I'll put a reminder, but remind me in case I forget after this is over. Right, thank you. Yeah, but Q is the charge which is minus E. So this is P plus Ea by C. And typically it comes in with as a squared. So in here, A is the vector potential, and in terms of the field, we'll write it. So there are many ways to have A's, which will give rise to the same H field. But I'm using this particular. This is a cross product. When you have vectors, you know you can have a dot product or a cross product. So this is a cross product. Okay, and so then you can verify it. So students, this is the first minor exercise you can do. Please verify that H is indeed del cross A and that divergence of A is 0. You have to verify this, okay? This is an exercise. It's called a mild exercise. It won't strain you too much, but it's good that you do it, because if you do it, you get a hang of it. Okay. Now, the spin contribution, of course, is exactly what you saw in the earlier lecture, namely G naught H mu B H times Sz, where Sz is half of the Pauli matrix. Pauli matrix. Have you all heard of Pauli matrices? Sigma Z is simply 1 minus 1 with 0, 0. Sigma X is 1, 1, 0. You don't need it today, but okay. But Pauli matrix. Okay with you all? Okay. And I'm talking about a single electron so far, one electron. So recall the setting. We have a Hamiltonian, okay, but if you had maybe with many electrons, but we are talking about the effect of the field on one electron at a time. There are many of them. We'll add it up later. Okay, fine. And so these are so this is delta H, change of the Hamiltonian due to spin. This is the change. The change in the kinetic energy will cause a change here. So that will lead to, okay, since this is kinetic energy, we'll just call it T naught. There's a divided by, okay, let me call it T. T is the usual thing we use for kinetic energy, right? So capital T, not temperature, 1 over 2m. So now I'm adding up contribution for all electrons, Pi minus E by 2c R cross H. So I'm substituting for A squared. All right. Now, are you all able to expand the square? What is A plus B the whole square? Somebody tell me. Not if A and B don't commute. Okay, tell me the answer if they don't commute. So the way you do it is write A plus B twice. So you get A squared plus B squared plus AB plus BA. Okay. Now what doesn't commute here? R and P. They don't commute. They're quantum mechanical. Therefore, when you expand the square, you have to be careful. So my advice is be careful. Do it. This is mild exercise number 2. Do it. Expand this and show that this can be rewritten as T naught is Pi squared, the ordinary T naught. I'm not writing the definition, but you understand. Plus mu B times L dot H. I should write Li dot H. Okay, I wrote a sum, so then I should write a sum here. Plus one more term, that is the A squared term. And that turns out, so now I'm going to assume that the field H is pointing along the z-axis. Is that okay? Where does that enter? That enters here, here. So if A is along the field is along the z-axis, A will involve x and y. Okay, so it turns out if you expand out, you find this is E squared over 8mc squared, H squared, sum over I, xi squared plus yi. Actually, maybe I should not sum over I. Okay, think of it as a single electron because I have to change my origin every time. But all right, something. Now, this is very nice because if you wanted to find the full change of the Hamiltonian, you would add the other one plus G naught mu B H Sz, Siz, and sum over I. Being a little careless in my coefficients, you'll forgive me and you'll set me right. So is the whole point clear? This is the change of the Hamiltonian due to putting on a small or big magnetic field. Okay. But remember, we are doing this in the context of some strongly interacting electrons in an atom. I have a single atom. These are electrons in some shell. It could be a 3D shell. Are you all familiar with the notation? 3 is principal quantum number. D is what value of L? Sorry? 2. SPD. 2. Yeah. So, okay. So, you could have a few electrons there. But remember, they're in the same shell. So, they're very close to each other. So, they're interacting quite strongly. So, the Hamiltonian really, in the absence of the field, will be primarily that. It will be that. Now we are asking what is the effect of this. Okay, so I just wanted to make that clear. So the first thing we have to sort out is what happens in a single atom. How are the things organized there because of the strong Coulomb interactions between electrons. Okay, I hope the logic is clear. But now I'm going to be nonlinear. I'm going to jump to something else. So we'll come back to the atom. In fact, that's the principal thing I want to address. But I'm going to come back to this other point we said, because that will actually enter into the physics of what is happening in the atom. And that is the point of exchange. Chandan mentioned Hund's rules. Some of you may remember Hund's rules, some of you may not, and others of you may not even have heard of them. We'll tell you what they are, but they come from, where do Hund's rules come from? If you read the book by Coe, he says that Hund found these rules purely empirically. So we are amazed because these rules really hold very well. But there is a justification we have today for Hund's rules, at least the first Hund's rule. And that justification relies on exchange. So that is why I want to first take up exchange. We will come back. Now, before you blast me again, I should have said, this is in quantum mechanics. The point made is that if we had the same problem in classical mechanics, there would be no magnetism at all. The reason is that when you write down a Hamiltonian like this, and you calculate a partition function by doing an integral over r's and p's, when you're doing the integral over p, e to the minus beta, this squared over 2m, it's a Gaussian integral, but you can shift the integration. This is a shift of the Gaussian variable, and you get the same answer as if there's no shift. So, which says that putting on a field has no effect in classical mechanics. And there's no spin in classical mechanics, so that's out. So this fact that in classical mechanics there is no magnetic response goes under the name of, somebody tell me? No, you don't know. It goes under the name of Bohr. Have you heard of Bohr? Yes. Good. And the other name is Van Leeuwen. Bohr-Van Leeuwen theorem. Miss Van Leeuwen, it's always cited as Miss, was doing her PhD with Niels Bohr, and he told her, go find the magnetic response of this. She came out and said it's 0. I'm just making up. So Bohr was a little shocked. He asked for the proof and he gave the proof. And since then it is called the Bohr-Van Leeuwen theorem, that there is no magnetic response in classical systems. Okay. He was very insistent that I cover this point here. Okay. But we are doing quantum mechanics, and that is different and crucial. Yes.
So the Hamiltonian that you wrote there, for writing that, you made a particular choice of A vector.
It won't matter.
It won't matter.
Yeah. Okay. That's a third mile problem. But that only you have to do. Okay. Tell us tomorrow. It won't matter. Show it. Show this. Yeah. Any other question? No. Okay, so we move on. Okay, so now I'm going to change, and I'm going to rub this out. Is that okay? Everybody taken down what they want to take down? You know, when I teach in TIFRH Hyderabad, some of the students don't, when I ask them, do you want to take down anything? They take out the camera and put. I mean, okay, this is technology. So I should tell you a little bit about the people associated with this development, like here. So one of the oldest books on magnetism, which is a very good book, and I would urge all of you to read this, is a book by Van Vleck. It's a little old-fashioned now. But in many ways, that was the first time that many scattered things about magnetism were put together in a book. It's called The Theory of Electric and Magnetic Susceptibilities, I think. Do you know? Anybody seen this book? It's something like that, the title. But Van Vleck was an amazing fellow. So I'm told that he would attend seminars, and in the middle of the seminar, he would sort of go to sleep. You know, I mean, would sleep. Okay, and everybody would say, there goes Van Vleck. But then at the end of the seminar, he would ask the most astute questions. So even while he was asleep, he knew what was going on. So I know because my thesis advisor was a student at the place Van Vleck was, and he used to watch. By the way, TIFR students might tell you that I also go to sleep in lectures. But I firmly deny that. So I'm told actually they take bets on when I'll go to sleep. But is that true? No. Okay, look at that. But the book by Van Vleck is actually extremely clear, and you know, if you can read it. It was written in the early 1930s. That is the time that quantum mechanics was just, you know, coming around. And books written by the first people in a field are usually the best because they've thought of all possible questions and they answer them. But see if you can get it. Okay, now exchange. Okay. What time did I start? So would I have sufficient time? I don't know where I am. I lost track. Half an hour's over? Okay, half an hour's over. All right, good. Fine. So let me talk about exchange. Now, it turns out exchange interactions of all types. You know, there's something called direct exchange or potential exchange, which is what I'll talk about. Then there is kinetic exchange. Very important. I hope I'll be able to talk about it. Then there is Zaloshinsky-Moria interactions. Then there is double exchange, Zener, etc. Then there are one or two other types also. And RKKY. And there are all sorts of ways that two magnetic moments can interact. And but this is the first, and in some sense, very important. It brings up, because it brings out the antisymmetric properties of the electron are responsible for exchange. And it's actually a very simple physical argument, but I'll give you the full derivation. So suppose there are two wave functions which overlap. This is phi A and this is phi B. Okay, as a function of R. This is B, sorry. Okay. Overlap is essential. If they're so far away that they don't overlap, no exchange. I mean, okay. And the sort of exchange that I'll talk about is called direct exchange. It also goes under the name of potential exchange because it comes from potential energy. And the first people to think about this were Heisenberg and Dirac. Some of you might have seen Dirac's famous book, Principles of Quantum Mechanics. He has one section, one chapter on exchange. You should read it. Very, very good. Okay, but I'm not following that. I'm just giving you something else. Now, suppose there are two electrons and there are these two wave functions. Remember, the electrons, if you did not have spin, then you could put one here and one there and be done with it. But since there is spin, there's also the possibility that an up and a down spin electron could be here or here. So the number of states is larger because we have spin. So how do you describe a wave function with spin? Well, there's the orbital part and there's the spin part, spinor. Spin, S-P-I-N-O-R. Some people say spinor, but I won't. Spinor. Okay, all right. Okay, fine. So we'll write the wave function as phi of r times, and the favored symbol apparently is chi of S. And chi will be, has two options. It's either alpha or beta. Alpha will denote up, beta down. Okay? Okay, good. So antisymmetry of the wave function will imply, okay, now we have to be careful. We'll look at cases one by one. Suppose both electrons are up. We'll write down the answer, etc., etc. Yeah, R1 and R2, correct. Yeah, so write this twice. Once put 1, then put 2. Right. This was generic. All right. Okay, but now I'm going to write right exactly what you want. So if both, yeah, so I'm 1 over square root 2 phi a of R1 alpha of S1 phi a of R2 alpha of S2. We just do it blindly. We write a determinant okay, what have I done? I put A column, A is the label of the wave function, and B in this column, sorry, in this row, and column, this is 1, electron 1, this is electron 2. So nothing complicated. Why am I writing a determinant? Because a determinant has the property that if you interchange two rows, you change the sign of the determinant. And that is exactly what should happen when you interchange R1 and R2, or two columns. Right? So because we want to have an antisymmetric wave function, and luckily we have only two electrons, determinant will work. But if one is up and one is down, what will the thing be? It will be very simple. Nothing to be afraid of. It's phi AR1 beta S1, for instance, phi of R2 beta S2 phi B of R1 alpha S1 phi B of R2 S2. these are wave functions, fine. But we want to know what will these, what is the effect of interactions of the two electrons in these wave functions. Okay. Have you understood the point? For instance, these could be two electrons in the same shell in an atom. Okay, yes. So, okay, because there are two, and when I switch 1 and 2, I need to change the sign of the wave function for me. One simple way to do that is to write a determinant. Okay, right? Now, what was I saying just before this? No. Anyway, I've lost that. It doesn't matter. Okay, we'll come back to it. I mean, something will happen. Yeah. Yeah. No, so, yes. The alphas and betas in the same, yes. It is necessary because the wave function is this.
I asked, is it necessary is it necessary that alpha and beta have to be in the same row?
Well, with my convention, yes, because this is the wave function row and this is the coordinate column.
So we can't have phi a beta and then the second element is phi
you
b
can't,
alpha.
because you're writing the same wave function and the wave function is this. The same wave function, okay? You can't do, Yeah. I mean, you can try it out if you want and see what you get, but it won't describe fermions. Right? Okay. Yeah. Okay, but remember what we're doing. We said we have two electrons in an atomic shell. Think about an atomic shell. What is the force the electrons feel? You have to think that way, otherwise you won't. First of all, there's the nucleus, which has a heavy positive charge. It's pulling things in and making Bohr orbits. So both the electrons are in the same Bohr orbit, and then the same. So now we are saying what is the effect of the interaction between electrons. But that is sort of sizable, but much smaller than the fact of orbits. That is why we wrote down those wave functions first, phi. Those are the, if you like, the things that are paramount. For those of you who are familiar with perturbation theory, we are doing perturbation theory. So the interaction is E squared over R12. And we are substituting into the unperturbed wave functions and asking what is the answer. So, fine. So that is the program. Let's just do it. All right, so let me, okay, since I'm running a little bit out of paper, let me, okay, I can use all this space here, right? Now, okay, I forgot to give these functions names. Let me call this psi1. This I'll call psi2. Psi1 and psi2 are two electron functions. They are wave functions describing two electrons, each of them. But clearly we could have psi3 and psi4. Okay, but psi3 is not going to be very different from psi2. Okay, one will be down, and you can figure out where will go the beta and where will go the alpha. I mean, so it's not very intrinsically very different. And psi4 will be psi1. Both are down. Wherever you see alpha, you write. Okay. So psi3 you can get from psi2 by interchanging alpha and beta, and likewise psi4 from psi1. Therefore, I'm going to content myself with writing only psi 1 E squared over R12 psi 1 and an explicit formula for that. So, what is it? Well, here we go, half integral dr1. This is understood to be a vector integration over three-dimensional space. I am not writing vector signs, I am not writing d3r because I am lazy. I am just writing dr. Okay. Integral dr1 dr2. Okay. So, what will we get? Phi a star r1. I am going to write this out in, by the way, I am getting 1 over 2 rather than 1 over root 2 because I am going to multiply two wave functions. Okay, so phi b star r2 it's not over. Okay, so this turns out to be CAB minus JAB. I'll write down now what C and J are in terms of these integrals. So, CAB is, as you might think, it's the ordinary charge contribution, okay, which is integral dr1 dr2 mod phi squared. As you know, mod phi a squared will give you the actual charge. I mean, what the probability. It's not the amplitude; it's the probability. Phi function, it's like the amplitude. This is mod phi squared. This is a. This is phi b squared over r12. I hope I have all the factors right. JAB is the exchange contribution. So, where did this come from? This you took this with this and you ended. Same sort of term. But now we will take this with that, which is exchange. You interchange R1 and R2. So, the whole point is that. So, there is an extra contribution JB equal to E squared integral dr1 dr2. Okay, now what you get phi r1 phi br1. It's like an overlap charge density by something like that. Okay. Sorry, this won't go further, right? I'll write it on this line. Multiplied by A of R2 phi B star divided. Okay. I would suggest note at least this down. I mean, this is important. But the rest, I leave it to you to.
So I see what you did over there. One question that I have is, you have phi A and phi B, which are wave functions of the two particles, and now you're interchanging the particle, and that's why you're getting R1, R2 on phi A, phi B, the mixing of.
But including the spin. I mean, with the
yes,
spin.
including the same My question is, how would this be in the case that the particles are indistinguishable?
They are indistinguishable. That's the whole point. Fermions are indistinguishable particles. You know, they're indistinguishable, but the wave function has the property that if you interchange any two particles, even in a many particle wave function, the whole wave function, maybe a wave function of 10 to the 23 variables, will change sign. So they're indistinguishable. Will change sign.
Okay, all right, thank you.
All right. Identical particles are either bosons or fermions, and they have different properties under interchange. Okay. Right. So we wrote this. Psi 2 is squared over R12 psi 2. Now, will this be the same answer or different? Psi 1 and psi 2 are actually quite different from each other. Psi 3 is like psi 2. Psi 4 is like psi 1. Psi 1 and psi 2 are different. Look at that, you will see. So the answer turns out to be simply JAB, I think. No? Yeah. Plus JAB. That's also equal to psi 3 E squared over R12 psi 3, and this one, by the way, is also equal to psi 4 E squared over R12 psi 4. So from two of the wave functions, we get one answer. From the other two, we get another answer. So how do we put this together? Well, we write a matrix. Yeah. Fortunately, there's just about enough space to write the matrix. Huh? Okay. Are you all having a problem with this portion of the board? No. Oh, you're talking about the students? Students, is this visible? Yeah. Nowadays, if you ask everybody will do this. What's this new thing? I mean, even if you send a message on a phone, you get okay, thank you. Anyway, whoever it was who did this, thank you. Okay, so how large is the matrix going to be? How many states do we have? We wrote them, I mean. Yes? Were you going to reply? No. Thought you right. 4, 1, 2, 3, you label them. I mean, okay. So 4 things have to fit here. All right. So we write them 1, 2, write psi 1, psi 2, etc. We forgot to do one important one. Yeah. We have to look at the psi 2, psi 3. Okay, sorry, this was what I quoted was wrong. Please correct. This is CAB, not J. This one is JAB. Okay. What is psi 3? Psi 3 is gotten from psi 2 on changing beta to alpha and alpha to beta. Okay, please note that down, I didn't write it. Psi 3 is gotten from psi 2 on interchanging alpha and beta. psi 4 is gotten from psi 1 on doing the same. Okay, yes. Yeah. Question?
Sir, if it is psi 4, then we have to consider two electrons are parallel to each other.
Yes.
One
Downspin. Correct. Right. Okay. I mean, I didn't write it, but yes. But that's exactly right. What you said is absolutely right. Okay. Yes. No, we've included this one. Right. Same, that's okay, but here it is. Here is the wave function. I mean, the wave function is explicitly here. So you can expand the determinant. This multiplied by this minus this multiplied by that. Right? So instead of this thing, you'll have something else. That's correct. Yeah, yeah. So you have to contract the spin also. So alpha and beta, when you contract, you'll get 0. Remember that. So, okay, so this I forgot to say. It's an important point. Thank you. So when you contract two things, I mean, which have a space part and a spin part, okay, so you have another one with a space and a spin. So space and space you contract. By contract, means you do the integral. And this and that, you do row column multiplication of 1 0 with 1 0 or 1 0 with 0 1. And you will get either 1 or 0. So you have to do that. Therefore, this mild homework is actually a very good thing to do. Okay? Right. Okay. So I'm sorry for the mistake, but that's what it is. Okay. All right. So now we are in position to write down 1 1. Somewhere we wrote it. Anyway, you will get the board CAB minus AB 2 2 CAB. But remember there's a 2 3 matrix element which is JAB. There's a 3 2 matrix element likewise which is JAB. This is CAB. Everything else is 0 here. And the last one here is CAB minus JAB. So now this is a 4 by 4 matrix which you have to diagonalize. I'm confused about which remark. Why don't you give it? What did you want to say? I'm not sure.
Like you are writing the perturbation in the matrix.
Yeah.
So maybe you can
actually,
say that why you are doing
the
that.
The reason I didn't say it now is because I said it earlier. But I think you missed it. But I will say it again. Remember what we are doing. These are 2 electrons, as I said, in one shell. The strongest interaction there is the field of the nucleus. That is the size. What we are doing is treating E squared over R12 as a perturbation on that. And the way you do perturbation theory is if you have degenerate states, you put in the perturbation and form the determinant. I think that's what you wanted to say. And diagonalize it. So the remark is absolutely correct. What we are doing is actually tantamount to first order perturbation theory. It's much stronger because of Z. Yeah, but a number which can be 50. for one thing. Okay, let me leave it at that. Okay, yeah, so I think, yes, for instance, if you applied this to helium or something, this would be not as good an approximation as if you applied it to manganese or something. But manganese has other complications which we are coming to now. Okay, all right. So, are you all okay with this? But now, students, would you be able to diagonalize this matrix, you think? Actually, you don't have to diagonalize 4 by 4. It's only the 2 by 2. Does anybody know how to diagonalize 2 by 2 matrix? How? Secular equation? Well, something you do, no? You know how to diagonalize. I think, what I've observed is that if I write a 2 by 2 matrix on the blackboard, by the time I turn, people have diagonalized it. I mean, it's like an automatic response. 2 by 2 must diagonalize without knowing why. It reminds one of Pavlov. Do you know Pavlov? Yeah. Look it up. Pavlov. Okay. But it's in this case, unlike Pavlov, this is a very good response. If you have a matrix, diagonalize it. Why not? Okay. So, what I'm saying is you have to diagonalize only this matrix. This is a very easy matrix to diagonalize because it's a constant plus j times sigma x. The values are plus. Anyway, you diagonalize this immediately. So, what are we learning? When you diagonalize this, the eigenvalues turn out to be CAB. One eigenvalue turns out to be CAB minus JAB, obviously, and the other one is CAB plus JAB from the 2 by 2. But look at this. This is the same thing that you had from here. So, as a result, you have 3 states here, degenerate, triplet, and then you have a singlet. Okay. So, this is the answer, that you have the Coulomb interaction E squared over R12 arranges the 4 degenerate states into one triplet and one singlet. Now, this is actually very important, but little, is it mystifying or not? It's not. Why is it? Okay, so let me add for some clarity that this is the state that goes with the eigenfunction, which is up down plus down up, symmetric in spin. So, what is happening is very simple in physical terms, and so let me therefore explain it. We'll use this figure. I happily drew 2 wave functions. This is not symmetric, nor is it antisymmetric. How would you form an antisymmetric wave function from this? Well, you do something, psi A minus psi B should do it, no? So, what will it look like? Well, since we have the luxury, we'll use colored chalk. So, it will look like if you see what I mean. Is this roughly right? I think something like this, yeah. Antisymmetric wave function at r equal to 0 will be 0. Clear? If a function changes sign, when you change r to minus r, it must be 0 at the origin. But if it is 0 at the origin is where you pay most repulsion for E squared over r. Therefore, you're avoiding paying any cost for that because you've made the wave function 0. So there is no probability of getting too close. But what the penalty for doing this is that the spin part must be symmetric, because the total wave function is antisymmetric. Space part is symmetric, and so antisymmetric, so the spin part must be. So, conclude, the spins are doing something guided really not by themselves. They're doing something for somebody. It's altruism. Why? Because by being parallel or symmetric, they're allowing the wave function to go apart, and therefore they're minimizing the energy. And this theme will come in again and again and again when we discuss different types of exchange. Spins will do something, they're just a label, but the labels arrange themselves to minimize space part of the energy. Okay, so this is the model. Okay, so let's leave it at, last point, very important. Okay, so okay so far? All right, now I'm going to rub this out. So let's summarize. Well, the summary is right here in this part. But we can write the answer in terms, purely in terms of spins. Now that we know this is the answer. Okay, and so how do we do it? Okay, let me write the answer first. So let's say this is the energy of the singlet, Es, the energy of the triplet. There's some formula with C and J, but let's not bother. So I'm saying the answer is Es plus Et over 2 minus Es minus Et over 2. Let me write it and then we put in some explanation. S1 dot S2 plus half. Okay, I've written in some odd way. Okay, to understand why this is so, notice that this is the same as S1 plus S2 the whole squared minus 1. Okay. Now I'm going to use addition of angular momentum. S1 and S2 are both spin half. So what values can S1 plus S2 take? Anybody? If I have two angular momenta, spin half. Now I'm adding angular momenta. What are the possible allowed values of J? Yes, 0 and 1, correct. So this can be either 0 or 1. 0 will correspond to singlet. 1 will correspond to triplet because there are 3 states with S equal to 1. So if this is 0, you'll get some answer here. Okay, and one more mild exercise, do it. And you read off. Okay, so you can put everything in terms of CAB and JAB and so on. So this becomes, if I've done it right, I don't know, CAB minus half JAB minus 2 JAB S1 dot S2. Okay. So constant, which is unimportant in an energy, minus this. This is the crucial bit. So everything we did can be summarized by saying that the effect is that of S1 dot S2. S1 dot S2, if you just look at it intuitively, will be, I mean, there's a minus sign, so you lower the energy by making spins parallel. If the spins are parallel, space wave functions are anti-parallel, which is good, it lowers the energy. Yeah, there's a question somewhere. No? Yes. Wait. Go ahead.
So as you can see, CAB is always positive because it's like the integrand is always positive. But can we comment anything about the sign of J?
I think you can. Offhand, I don't know. I mean, suppose you take, well, simple case, think of two real wave functions. Then it's positive.
I mean, if it's a delta potential, then I could see that it should be positive. But for long range,
Yeah.
then
Okay. It's a good question. I don't know the answer offhand. Does anybody know? We don't know at the moment.
Thanks.
We leave it
Yeah,
to you to
find
find
out.
out. Okay, sorry. Yeah, but typically it is positive. I mean, yeah.
Am I right to then assume that if we take the anti-parallel case, then we will have plus 2 JAB S1 dot S2?
No.
No.
This is the answer which includes parallel and anti-parallel in it. This is the answer. This is the answer for the full Hamiltonian. S1 dot S2 itself, where did it go? Where did we derive that spin Hamiltonian? Ah, here. S1 dot S2 itself is this. So S1 dot S2 can be, okay, you have to -1 or 0, right? Okay, so remember it's an operator. S1 dot S2 is an operator, and you have to ask for its eigenvalues. You can't think of it classically. Okay, so now I'll begin. How much time? 20 minutes. 4:20? That's 5 minutes long. Oh, you're going by that? Okay. All right. Okay, I'll have some water. You'll take a water break. Have water. So this was an interlude. We are coming back to the question of electrons in atoms. Okay. And so let us see what happens. Something in the flooring. No, you can't attend to it now. But yeah, if you can put a large amount of Fevicol and sort of, yeah, because somebody in principle can trip. In practice, did you notice it? Oh, maybe I'm walking around too much. Okay, all right. So I'm rubbing this out, and we're coming. Can I rub out? Yes. Yeah. Question. How does what?
How does momentums line up in triplet state, parallel or anti-parallel?
How does the moment line up in a triplet state? Okay, so what is the triplet state? It is these are the three, and I presume you're asking the question because of this, because here it is sort of clear. Okay, so what you have to notice is that this state is a spin rotation of the state. So let me put here, I mean, we're using Z, of another state which is along the x. So the two spins are actually parallel along the x direction. I hope I'm right, I'm making it up, but I think it's right. So, yeah, let's see. So, yeah, I can't do it in my head, but I think that's the answer. So, they are always parallel, but they're not parallel to the z-axis. I mean, you know, it's partly and partly parallel. It's a quantum state. But I think it's just this. Rajiv, do you know? Okay, we can, it's easy to check or disprove. Let's leave it till after the lecture. Okay? Okay. Fine. So, the answer is that in a triplet state, they are in some sense always parallel, but parallel. They're always parallel, up, or down, both parallel, or in the xy plane, but still parallel to each other. The best thing is take two colored chalks and try it out. Okay. So now we are back to, so this point that I've been emphasizing and that has been emphasized by one of the people in the third row over and over again is that we are doing perception theory. Yeah. So what is going on in this? So let me once and for all tell you all. I don't know if this makes sense, but okay. So we are writing a big fat Hamiltonian. So far we've been talking only about H1. Okay. H naught is sum over I pi squared by 2m plus sum over I u of Ri. This is the central force. U includes Z, the atomic number, and everything, Ze squared, etc., etc. You have to be careful because there's screening from inner electrons also, but we're assuming a central force, and this is the biggest of everything, order of 10 electron volts. How do we know? Somebody knows the ionization energy for hydrogen? 13.6 eV, so that's about 10. So that is the energy scale here. H1 is half Coulomb interaction. Next in the order of bigness, it's order of, I don't know, I'm just making a sort of guess, 2 electron volts or less. H2 is what is called spin orbit coupling. And this is 0.1 eV at most, well, half of that. I couldn't hear. Yes, yes. Yeah, it's actually of the same electron, if you notice. Li dot Si. So be clear on what we are doing. We're writing such a term for every electron. You're soon going to see the effect is going to be that there's a massive capital L and a massive capital S produced. And they are coupled by some, not zeta, but lambda, capital L dot capital S, and we'll derive a formula for lambda. Okay. So this is the hierarchy. Fortunately, at least for the rare earths, that is the actinide series, the lanthanide series. Lanthanide series, this is the order in which we go. In other words, H0 is bigger than H1, H1 is bigger than H2, H2 is bigger than H3. Therefore, the strategy is to look at this. You solve it by assuming it's a hydrogen-like, NL, etc. But you have horribly degenerate wave functions, especially if you have many electrons. So then you put this in and perturbation theory. Then you get an answer. But this is much lower than that. You still have a lot of degeneracy left over. Apply perturbation theory, you lift that degeneracy. Then you have what is called multiplets, and then crystal fields, I haven't defined them, but the effect of the surroundings in the solid will lift that degeneracy. It's actually justified because of the magnitudes. Okay, so the way functions are called configurations. I mean, this is spectroscopic notation. The way after you're done with this are called terms. And after you're done with this, they're called multiplets. So these are the bunch of Li's. So these are categorized by capital L and capital S. These are characterized by some J. And crystal fields will lift that degeneracy within the J manifold also. However, this is not true away from the rare earths. What are the rare earths? Can somebody name me 2 rare earths? Somebody from that back, yes. What was it? I couldn't hear. It was correct. Dysprosium and gadolinium. Yes, very good. Yeah, so that's right. So the rare earths are unfilled 4F shells. You remember that. But before you come to 4F, there's 3D. Name 2 elements from the 3D series. Name. Transition metal is not an element. Iron, sorry? Nickel, zinc, copper, very good. The whole lot. Good. That's very good. But what happens is the following. Imagine a 3D shell as contrasted with a 4F shell. 3D also has 4s electrons. The 4s electrons go and do the bonding outside. 3D is unfilled. It's an unfilled shell. But the wave function of 3Ds are quite extended, I mean comparatively. So they are very susceptible to outside influences of the crystal fields. Meaning that if you have some oxide or something, Fe2 or I don't know, something, and you have oxygens, they'll be charged and they will produce a very strong electric field here. So that is the crystal field. So in the case of transition metals, this is stronger than that. So after this, you have to treat these and then that. Okay. So I'm just warning you, there are 2 cases. Okay. Now, we'll end with one last picture. I have 2 minutes, so I'll just take 2 minutes. So, what are the eigenfunctions of H naught? The phi of r equal to some radial wave function n. I'm just writing hydrogenic type terms times y of omega. Omega the angular coordinate, right? And what we do is now, we don't actually need this. We're going to, no, we need this because N and L will categorize the energies. The thing is, I need some space. So, okay, the last thing I'm putting on the board, but it's 1, 2, 3, 4, 5, 6, 7. Okay, so here we are, n equal to 1, L equal to 0. What are the two elements that sit here? Hydrogen and helium. Then we're just filling hydrogenic levels. N equal to 2 will come next, and it will have L equal to 0. There's also an N equal to 2 with L equal to 1. But remember, the energies are degenerate. Or, no, L into L plus 1 will come in, no, somewhere. I think they're not degenerate. Yeah, this is higher. So the two elements that come here are lithium and beryllium. Okay. With this, you have a bigger degeneracy. So you have boron, carbon, nitrogen, and oxygen, fluorine, and neon. 1, 2, 3, 4, 5, 6. L equal to 1 has degeneracy 3, spin 2, so it works out. Yeah. Then we come to, I'm doing this because there's a point. I mean, suddenly you'll see something. L equals 0. And here you have nicely sodium and magnesium. Okay, then you n equal to 3, L equal to 1, you have aluminum, okay, a whole bunch of them, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay, now watch out. What should happen here? You should get n equal to 4, L equals 0. No, you should not, no? You should get n equal to 3, L equal to 2, but you don't. So this is the point, right? This is why you're getting to these unfilled D shells. So, okay, I'm just going in terms of the periodic table. What do you have? Okay, next comes potassium and calcium. Okay, so you don't go to L equal to 2, but now you do. L equal to 2 is the D state, is it? Yeah, okay, I have to keep counting. Yes, it is. So, for a while the D's didn't make it. You went to 4. But now the D's come back. So, here are the elements. And so, here I'll just write them here. Oops, there's not space. And then we'll stop. So, sorry, I'll just stop in a minute. Scandium, titanium, vanadium, chromium, manganese, half the shell, iron, cobalt, nickel, copper, and zinc. Okay, so I'm not writing the fillings here. Okay, 3D, 3D2, to 3D5, 3D6 here, all the way to 3D10. Okay, let's leave it at this, but I just wanted to point out the following fact, that we have an unfilled shell as we go across the elements, and therefore unfilled shells will very likely have moments. So the moments or the magnetic properties are largely due to unfilled shells. The first time we encounter unfilled shells in the periodic table is with the 3Ds. We encounter them again later with the 4Fs. But unfilled shells are important. Because if you have filled shells, the whole shell is full. There's no orbital angular momentum. Everything, ML is compensated by its negative. Spin, so if you have a filled shell, the only magnetic response of a filled shell, by the way, there is a response, is diamagnetic. I forgot to tell you all that. That x squared plus y squared term, it's a negative susceptibility, which was what was pointed out by Chandan. Why is it negative? Because you remember that x squared y squared term came with a positive sign. So the energy went up when you had a field. So, ergo. I think I'll stop now. Of course,
query, sir. Why s orbital electron?
sorry?
Why s orbital electron do not contribute to the magnetism, where we basically talk about magnetic moment of electron that rises from d orbital.
S orbits?
S orbital. Because since only L is equal to 0, then that is not contributing to the magnetism.
S will not contribute, but S can contribute, like hydrogen. I mean, but see what happens with hydrogen. Okay, so yeah, so if you have, the thing is hydrogen goes and forms molecules. If you had a hydrogen atom, it would surely respond paramagnetically. Zeeman splitting is there, exactly. Zeeman splitting is the hallmark of a response, positive response to a magnetic field, and it is there. But as you cool, hydrogen goes and forms a molecule, and the molecule has compensated spins, overall 0. So no further response. Helium, of course, is full shell. So
how about things like tritium or
tritium,
the nucleus?
or even deuterium.
Oh, deuterium even.
Yeah, but those are nuclear properties. They don't do anything. They change the size of the shell. I mean, because Z will change. Oh no, Z won't change. N more neutrons. I suppose nothing much happens. I don't know. Yeah. It will be different.
The spin orbit coupling will change.
Why? Okay, that will be different, yes. Okay, we haven't discussed hyperfine interactions. Yeah. I always get mixed up with fine structure and hyperfine structure. Hyperfine is due to nuclear, no? Okay, does any nucleus have a spin? But then why do we neglect nuclei? Why are we not talking about? No, not alpha. I mean, he knows the answer, but I mean, what is the formula for Bohr magnetron? M. So there's a factor of 2000 there, even between a single proton and that. So that suppresses the nuclear spin, but it's there. I mean, when you go into MRI machines, it's there. Yeah. Okay.
Any other questions, comments? Okay, thanks, Mr.
Is there tea?
There is no tea.
No, we want tea. I mean, sorry.
We'll get in, sir.
Okay, sorry. I mean, is it okay with you all if we have tea in the room?